So this is something, maybe some of you know about this, others, it's time to learn. And if you know about it, there still will probably be some interesting things I'm going to say. And so I'm going to talk about L1 norm methods for convex-cardinality problems. Actually, I think people have heard of things like compressed sensing, these sorts of things. Okay, all right, good. Then everyone take a look at it. Okay, so what I'll do first is just talk about what are convex cardinality problems. So I'll talk about problems involving cardinality. We'll look at a whole bunch of examples. Then I'll explain the basic L1 norm heuristic. It's a heuristic for solving these problems. These problems are hard. And then an interpretation of them as a convex relaxation or a convex envelope interpretation for these things. We'll see what this is. And actually, once you understand that, it actually puts you in a better shape to actually solve these problems better. We'll see that when we get to it. There are some interesting recent results from Donahoe, Candes, others like that, theoretical results about these things. They're absolutely amazing. And I'm only going to just mention them. I'm not going to dwell on them. In contrast, I'm going to focus on the whole thing as an idea and as a very effective method. It's a heuristic, but a very powerful heuristic. I'll then talk about the iterated weighted L1 heuristic, and we'll look at the extension to matrices, where instead of cardinality, you get rank, right? And this is something that's sort of very popular right now, and I think someone figured out that within, 200 meters of my office, there's like 50 people working on the same thing, which is decomposing matrices. It's like sparse plus low rank. So, okay, all right. So before I get into it, I'll say a little bit about the whole picture. So cardinality problems, I'll define it carefully in a minute. These arise often. Cardinality is just the number of elements, the number of non-zero elements in a vector. So these arise often, but they're hard to solve exactly in general. I mean, of course, there's some that can be solved, but in general, they're hard. And it turns out that there's a simple heuristic. It's just based on an L1 norm and various generalizations of this. It seems to work very well. So that's it. And this is although it's very fashionable in the last 10 years. In fact, it's been used for 50 or more. And it's been used in engineering for sparse design. I'll explain that when we come to it. It's the basis of something called lasso, which is something like least absolute sum something rather than something else. I don't know. And also robust estimation and statistics. It is in fact the basis of the support vector machine and machine learning for classification. In the 90s, it was used, a variation was used in signal processing and geophysics. It actually goes to the 1970s. And that's total variation reconstruction. And then nowadays, things like compressed sensing are very popular. And there are a few more, there's others, but I'm not going to add to this. I'll say something about these theoretical results, but I'm going to spend almost no time on it. Okay, so let's get into the details. So the cardinality of a vector is the number of non-zero components of x. By the way, some people write this as the L0 norm, right? So that's the other thing you will see. This drives me insane because a norm is a norm. It has been a norm since 1850, and so you ask someone what is it? Because it's not a norm, right? It's not. It has none of the properties of the norm are satisfied by cardinality. So I refuse to write this as a norm, L0 norm, and I refuse to say L0 norm. So if you look at other things, you'll see L0 norm, but I won't. I refuse to. Okay. It's a separable function. In other words, it's just a sum of functions. In fact, the card function of each individual element. But the card function is completely trivial. It's something, it's a function whose graph looks like this. 0 is 0, and then everywhere else it's 1. So it goes like this, like that. So it's very simple. Now, it has no, otherwise it really has no useful convexity properties. I mean, it's quasi-concave on R+, but that doesn't really help you unless you want to maximize the cardinality or something, but that's generally silly. Okay, that's the cardinality. So we have a kind of a vague definition, but it's good enough. So a convex cardinality problem is one that would be convex, except for the appearance of the cardinality function in either the objective or constraint. So, and they look like this. Here's the convex minimum cardinality problem. So you minimize the cardinality of x subject to x in C. That's some convex set. Okay, so find another way to say this is find the sparsest vector x that satisfies a bunch of convex constraints. Okay, so that's this. Or you can have a cardinality constraint. Minimize a convex function subject to x being in a convex set, but with the number of non-zeros of x limited to k. So you have a budget on non-zero. And so this often arises where you're selecting k out of n of something. Well, the examples will make it clear. Okay? Now, how do you solve them? Well, if you fix the sparsity pattern of x, so if you know which entries are 0, which are not, the entire problem becomes convex, and we can solve it easily. Right? So then that means you just solve all 2 to the n convex problems, and you're done. Right? So actually, this is entirely possible for n less than 10. It's fine. And in fact, you could probably do it. You could probably do it for some other cases if the problem is small enough. If you go up to n equals 20. And in fact, from the material we did yesterday, you would know that. So, for example, at n equals 20, this would require solving 1 million convex problems. And from yesterday's lecture, you know that if the problem is a small QP or a small LP with a couple hundred variables, I can solve 1 million in under a minute. Because it takes me 60 microseconds to solve each one. Okay? So, in fact, that's not even right, because I can run a whole bunch of them in parallel, I can run them on 8 cores, and I'll do it in 10 seconds. Okay? So, yeah, you know, but if the problem is bigger, you know, it depends on the size of the problem. Okay. Now, the general problem is NP hard, right? Which, you know, it means something, but don't read more into it than it deserves, right? It means precisely that, from a theoretical point of view, it is as hard as many other problems which are thought to be hard, but not yet known to be hard. Okay? I mean, it's quite likely that they are hard. Okay. And of course, you can solve this problem by branch and bound, or any other method of, well, there aren't really any other methods that work. So, any other method of global optimization. So you can solve it. And if you're lucky, it will take less than 2 to the n. It solves a convex problem to solve the problem. Yeah, so that's it. But in the worst case, it reduces to checking all of these. Okay, so, all right. So let's just get out let's get out of the way the NP hardness. So here's a Boolean linear program. It says minimize a linear function. And you know what? You don't even need this. Just the feasibility problem too. So you don't even need an objective. Okay, it's this. It says find a 0, 1 vector that satisfies ax less than b. You don't even need an objective. It's irrelevant. Okay, that's NP hard. In fact, that includes the most famous of all the classical NP hard problems. That's 3 sat instantly, right? Because you just encode that with each row of A as one of these ORs. Has 3 non-zero entries and so on. So you can easily arrange 3 sat, traveling salesman, anything. You can embed any of these problems into simply solving Boolean linear programming feasibility. Nothing else. Okay? So we'll represent it as a cardinality problem. I mean, this is silly, but you know, just to get it out of the way. Again, you don't even need the objective. It's totally irrelevant. What you do is you write this. You write ax less than b, and I write card of x plus card. In fact, think of a single point, right? If you have a single point, then card, if x is a scalar, card of x plus card of 1 minus x, well, it's either 0, 1, or 2. It can't be 2, because then if it was 2, it would be, sorry, it can't be 0, because that would require x to be both 0 and 1 at the same time. So it's either 1 or 2. And it's 1 if x is exactly 0 or 1, and 2 otherwise or something. So this is equivalent to saying x is 0 or 1. Okay? And so we're done. That's taken care of. Okay, now we're going to look at applications. This is much more interesting. Okay? And I'm just going to go over broad classes of applications of this type of stuff. By the way, I haven't said yet how you solve these. The only thing I have said is that these problems are at least as hard as other problems, which are very hard. Right? So we'll move on. So one is this, is you have sparse design. So you want to find the sparsest design vector X that satisfies a set of specifications. And the idea is that zero values in X simplify the design, or they correspond to components that aren't needed. And here are some examples. So one would be things like FIR filter design, if you're going to implement, well, it could be in software, but say you're going to implement it in hardware, right? A zero coefficient is one for which you don't have to implement a multiplier, so for example. Antenna array beamforming, so that's very interesting. You have a bunch of antenna array elements, and there you have weights that you're going to combine them to get a beam shape, so you want to receive a signal from this direction, but not from these directions, right? And so that's a convex problem. But there the idea is if you have a sparse weight vector, a zero weight vector corresponds to an antenna element that you don't even need. So the way you do this is you take a problem, you make an array. You don't intend to have 1,000 elements in your array, but you make an array with 1,000 elements. You solve to the extent that you can a convex cardinality problem, and you're hoping that it picks 22 of the antenna elements, the weights to be non-zero, and so basically that designed the geometry of your antenna array, right? In truss design, that's a very famous one. You have a truss or a space frame, so you have some mechanical thing with nodes, and you have bars connecting them. And the variables are the cross-sectional areas of the bars. Those are variables. So if a bar has cross-sectional area 0, it means it doesn't exist. And so what you do is you take a bunch of nodes and you have way more bars in it than you intend to implement. So you have a million bars would be very common. You solve one of these problems, maybe approximately, and the hope is you get something like 125 non-zero bars, and you just design the topology of your structure, right? So this is the idea. Wire sizing, you do something like you make a power supply distribution network on a chip. Your variables are the widths of the wires that run out. It's of course not a tree, because if it's a tree, you can't have any wire be 0, because then you've disconnected the power. So if has to be a mesh or something like that. And then when you solve a problem like this, it will actually design an optimal, it will choose an optimal tree or something like that. Okay, so this is sparse design. And there are many, many other applications in that area. It's a huge deal in statistics and data modeling. It's huge. So here it is, and in fact, David Donahoe goes around and sometimes says L1 is the least squares of the 21st century. So, and by the way, it could be true in the sense that everyone is working on it. Everyone in statistics and machine learning and things like that, everyone's working on it. But in my opinion, a lot of that is academic herding effect. You know what herding is? That's when a bunch of animals kind of go together in a herd. Right? That's it's intellectual herding. They look around, everybody else is working on L1, why shouldn't they be? And so they are. So okay. All right. So here's a very famous one. Is regressor selection. So if I minimize norm AX minus B, it says fit B with a linear combination of the columns of A. So the columns of A are called regressors, and you just want to fit it this way. As of course, well, that's basically the oldest convex optimization problem there is. It's the most widely used one too. But here you say I want the cardinality to be less than K. Okay? And so that says I give you a whole bunch of columns or regressors, and I say, please fit B, but don't use more than K of these, right? So, of course, you can solve this by trying all n choose K choices. Now, if K is small enough and n is small enough, if this doesn't bother you, go ahead. If this is if n is 100 and K is 3, you could do it. You could just enumerate all the choices, right? And the idea is it chooses a set of the regressors that together best fit or explain B. You do not get the answer by doing a stage-wise regressor selection. Right? That's where you take the one that fits the best, then the next best, then the second, this kind of thing. So it's also called regressor selection. And variations would be things like this. find the smallest subset of the regressors that gives an error on the training set less than epsilon, something like this, or minimize this, or show them the trade-off curve. By the way, this is just for least squares, but this holds for any machine learning or statistical model. Most of those, by the way, of course, in fact, the vast majority of them, the ones that are used, are actually based on convex optimization, right? So logistic regression, softmax model, support vector machine, you can go on and on and on. The ones that are actually used, generally speaking, are convex optimization, and so they all end up looking like this. And in fact, there's all sorts of cool things people do there. By the way, in some cases, what's of interest is actually not even the X, but which ones you select. Right? That's of interest. I'll give an example of that. So instead of an L2 norm, we take the logistic, the negative log likelihood for the logistic function. And so you're making a classifier. So you make a logistic classifier. And you add a constraint like this. And so a good example there is you have a genetic study. You have patients, maybe a couple of hundred of them because it's very expensive. Half of them have some disease or some form of disease, the other half don't. And for each one, you have gene expression data. That's 30,000 numbers. Right? So for each of 200 patients, you have 30,000 numbers. Okay? And the question is to make a classifier that separates the ones that have the disease from the ones who don't. Okay? So this is the idea. Now, obviously, there's many hyperplanes that separate, perfectly because you only have 200 points in R 30,000. So of course they can be separated, right? So the key is to make one that's sparse. And in fact, this is widely used. We'll see. The heuristic that I'm going to describe later is widely used for that. And in fact, in that case, what's often interesting is are not the numbers themselves. It's completely uninteresting. It's actually which were selected. So the way a gene study typically works, I have colleagues who do this all the time, is they take this data, they go through, they approximately solve this problem, and what happens is out of 30,000 genes, they say, here are 27 that predict, well, whether you have this disease or that. And then an actual biologist will look at it and say, these first 10, I am completely familiar with them, and I knew that they would be involved. This last 3, I have no idea. That's very interesting. I wouldn't have guessed that. Now, they don't believe it, which is good, because you shouldn't believe anything once you want this kind of stuff. They don't believe it, but then they make a phone call to their postdoc in the lab, and 1 week later they know if it's true or not. Right? They knock out a gene or something like that and see if it happens. Okay, so, all right. Okay. Signal processing, it's a huge deal. And I should say, well, I'll say a little bit. Let me explain what this is. So the idea is you have maybe something like a noisy measurement of a signal here, X, a standard noisy measurement. But you have the prior information that X is sparse. And I should explain a little bit about that. Usually A has 2 forms. It's the product of 2 things. It's a measurement matrix multiplied by what people call a dictionary. Right? So we'll just say that X is sparse itself here. And so you have a problem that looks like this, right? And so I can give an application. Well, let's do it. Here would be a typical application. X would be an image here, so it's big. It's 1,000,000 or something like that. And A would be even bigger. It's 1,000,000 by 100,000,000. Okay, and what it is it's called a dictionary, and each one is a little basic image. Like, for example, they have things called curvelets and things, or they could be little Gaussian, wavelets or something. I mean, it doesn't matter. There's a whole bunch of people blabbering on and on about this kind of thing, giving names to these things. But the idea is, you would say that, look, the actual images that people generate or use are typically sparse in that basis. So that would be the idea. And so this says, given an image Y, please choose if you're lucky, this could be 1,000 or 10,000, right? And then if you're able to do this, you've achieved huge image compression, right? Because instead of describing 1,000,000 numbers, the pixel values, you give 1,000, 10,000 coefficients, right? So that's the idea. you can also do things like estimation with outliers. So here you have a bunch of measurements. This is actually just like the robust Kelvin filter we looked at. In fact, that's the hint that's where we're going. So here you have a standard Gaussian noise, but you also have a noise here which is sparse, right? So this is something like a Gaussian plus sparse model. Another way to say it is if this is sparse, it says that whenever Wi is non-zero, Yi means nothing. That's the right way to say it. Because otherwise I don't constrain Wi, the value. Once it's non-zero, it just means Yi is meaningless. That's all it means. And that's an outlier, or it could be anything else. Okay. So this would be your set of bad measurements. And then if you want to find the maximum likelihood of X, you would solve this problem. You would minimize the negative log likelihood function. That's this, well, with a constant, multiplicate it and add a constant we ignore. But you sum that only over the valid measurements, right? And one of the variables here is, in fact, the set B, the set of outliers. And you can just write it this way. It's the same thing. So outlier detection and removal is another cardinality problem. Another one, more generic, is an optimization. I have a bunch of convex inequalities, M of them. And it's easy to detect if they are mutually infeasible. That's easy. Convex optimization problem. So we do that. If I find out that they're mutually infeasible, then I might like to do this. I might like to find an X that satisfies the largest number of these, or violates the smallest number. Okay? So that's, it might be you're doing engineering design, you have 50 specifications, it's infeasible. You're designing a circuit. You just can't do it. And because it's convex, it means that nobody can do it. It's not just you. No one can do it. Okay, so and then you say, well, okay, am I way out, or how many constraints do I have to throw out before I can meet my specification, right? And, you'd like the answer to be 3, so that you can meet 47 of them, and that tells you which ones you have to relax. Okay, so you might write it this way. You minimize the cardinality of T, that's another variable. Subject to Fi of X is less than Ti. You don't even need this. You don't need this. It's irrelevant. But the idea is if Ti is 0, it says that you satisfy the ith constraint. If Ti is non-zero, then presumably it's positive. And if it's positive, it says that you can violate the constraint as much as you like. Right? And if you take the cardinality of T, that's the number of ones you violate. Okay, so that's easy. And it's easy to figure out if you can remove 1 and so on. But in general, this is not easy to do. Okay, here's an example. Is linear classifier with fewest errors. So I give you data. Data looks like this. I give you a bunch. These are feature vectors in Rn here, and then I also give you a Boolean outcome or label. Like that, and I give you, this is your data, a bunch of these. And you label the points as +1 and -1, and you put them in Rn, and you look at it. And what you want to do is find a hyperplane that separates them, right? So whether there exists a hyperplane that separates them is a convex problem. It's an LP. That's been known actually since there was a special method, the perceptron made, which is the separation method, of course. Made to solve this, and people blabbered on and on about it in the 40s or 50s or something like that in the US, until it was much later than it should have been. Somebody pointed out this was a linear program, number one, and much later than that still did someone point out that their beloved perceptron algorithm is called the subgradient algorithm. All right. And a classification error is when this inequality, when this product is negative. It's when the sign of this is different from the sign of that. Right? And so how do you solve this? Well, you might, if you can't, you can check if they separate, that's a linear program. If they don't separate, you would like to find a hyperplane that misclassifies as few as possible. This is natural. And that would correspond to this. It says minimize the cardinality of T. This thing, by the way, is, of course, in machine learning, I think this is now called the margin. Fine, that's the margin. If it's negative, it means you're violating. If it's positive, you have some, whatever, you have some room or something. So In that case, this simply says it's a slack for the margin. This is homogeneous in W and V, so I can actually, without loss generality, make that a 1, right? And then, and you have this problem here. Right? By the way, this problem and a lot of others, it's going to turn out, you might think this is what you wanted to do here. That's the natural thing. It turns out actually very careful statistical analysis reveals you don't even, this is wrong. You were wrong. You did not want to do this. In fact, what you really wanted to do is the convex relaxation that we're going to get to later. I'll mention that together. Okay. Here's one a little bit more sophisticated. This says, I have a set of mutually infeasible convex inequalities. Now before we looked at the following problem. Maximize the number of inequalities that you meet, right? Or minimize the number of violations. This is a different one. This says the following. Find me a subset of these that is mutually infeasible. And you want that, you want the smallest one, because that's the most informative, right? If you give me 50 inequalities, we verify that it's not feasible. It's a very strong statement for me to say, the reason is that F12 less than 0 is infeasible. Just one inequality, it's a very strong statement, right? But it may be that it's more subtle. And in fact, infeasibility comes from interactions among multiple ones. And the smallest one is 10. Everybody see what I'm saying here? So it's actually the dual of the other one, right? And it's quite sophisticated to actually understand what this means and all that sort of stuff. So how do you do this? Well, you do it to the dual function. So the dual function is this. And if this thing is positive and lambda is positive, that's a certificate proving that that set is infeasible. Now, if lambda is sparse, then look at this. It says that it only uses some of the FIs. So finding the sparsest lambda that satisfies this actually is exactly the same as finding the smallest set of mutually infeasible inequalities. Okay? So it's very interesting because you try to do a circuit design, it's infeasible, and someone says, what's the problem? And you come back and you say, well, it's this. Of the 50 inequalities, it's the connection between the bandwidth requirement, the phase margin, and the power. It's those three. That's a very strong statement and extremely informative, actually, in practice, right? So, okay, it's like this. It's a cardinality problem involving a dual. Okay. Let's look at finance. Well, tons of problems here. They're all a bit silly, but that's okay. So you're going to purchase some amount of some asset, right? Say XI. The trading fee is the following. There's a linear trading fee. That's this. But then if you trade at all in an asset, there's a fixed fee. So that's your fixed fee, right? And I've just made them all the same. It doesn't have to be. You could make this beta transpose times card of X, or you overload card of X to be element-wise. It doesn't matter. So the budget constraint says this. This shows you everything. This is the amount. That's the growth. That's actually the amount you purchase here before fees. This is the fees you pay, and the total of these has to be less than your budget. Okay? So that's obviously a convex cardinality constraint, because without this would be convex. Okay? And you have a standard problem. Your mean return on investment is this, and your variance is that. And you want to minimize something like the, say, the variance, the risk here, subject to the mean return exceeding some minimum. And so you have a problem like this. And except for that, this is, of course, convex, right? So, and so another way to say it is, you're actually, in fact, in this case, what you're doing is you're saying select. Well, you're not really saying this, but you're saying you will be incentivized to select a small group of assets, because if that achieves the risk you need, small risk, and also big return. And the reason you're going to get one that's small is because the more assets you involve, the larger this is just wasted. That's just money you throw away, right? So, by the way, a variation on this is now a multi-trillion-dollar industry. It's index tracking. You know about index tracking? So the idea in index tracking is this. You want to track some index like Wilshire 5000. So you have 5,000 assets. The weights in the index change every day. The values return every day. And you want to replicate, well, possibly with a small error, the return of this index. Okay? But it doesn't even have to be an index. It could be anything you like. Right? So the way you have 1,000, 10,000 assets that you could use. So the idea is this. You construct a sparse linear combination of assets to track this non-sparse asset. Everybody got that? That's index tracking. You do that, and what will happen is your trading costs will be. One way to track Wilshire 5000 is to buy all 5,000 assets and every day do the trades, because the capitalizations will change every day and all that kind of stuff. And it'll be ridiculous because you'll just run up some giant trading fees. Right? So the idea is you make a sparse linear combination that tracks. Convex-Cardinality problem. Oh, and you might ask, is that how they do it? The answer is absolutely not. They do it using completely ad hoc methods. Okay. Let's look at fitting. Well, let's suppose you have a corrupted signal, right? I have a corrupted signal. I want to fit it with, say, a piecewise constant signal with k or fewer jumps, right? Now, if I told you what the location of the jumps are, then it's a convex problem. In fact, it's completely trivial. It's the average on each of the things, so it's even more trivial. But one way to do this is something like this. You take the difference matrix, the first difference matrix, and you write this as a convex-cardinality problem. So you're given this corrupted thing. X has what you're finding, and you say, please minimize the least squares fit here. Subject to, this constraint simply says X hat is piecewise constant with k or fewer jumps. And that's it. And so another way to say this is, this is also called segmentation. Because you have a signal, and you're actually breaking it into k or k plus 1, something like that, segments. And on each segment, it's constant. And so you're doing segmentation. So that would be this problem. Oh, let me remind you that not one of these problems can we solve. In fact, I showed you earlier, the only thing you know so far is that no one can solve any of these problems exactly. Right, probably. But we'll get to that, don't worry. The story will turn positive. Think of this part of the story as this. If you could solve these problems even approximately, there would be a lot of applications. That's the right way to say it. Okay, if you want to do piecewise linear fitting, it's the same thing. You take the Laplacian, or the second difference, and you get the same thing. And if you do this, you fit a piecewise linear fit. Right? A continuous piecewise linear. Okay, that's enough. I think once you get the idea, you will realize these problems are absolutely everywhere. Everywhere. And they're also in places where people don't even think about it. Like in all these machine learning courses, they teach support vectors, they teach all this nonsense about L1 regularization and things like this, and they never mention this. Because this is really kind of what you want to do. This is the precursor to that. Okay, so here it is. Here's the method. It's very, very simple. It's this. You take the cardinality and you replace it with a multiple of one norm. That's it. Or you add a regularization term of one norm to the objective. That's it. And you have a parameter lambda gamma, which is it's used to achieve the desired sparsity. That's it, right? So, and we're going to see it's not just a one norm. Although this is what people use. In fact, by the time this lecture finishes, you'll be much more sophisticated, because the correct thing to use is either a weighted one, or even more sophisticated, an asymmetric weighted one, where you penalize the positive and negative violations differently. And you'll see exactly what these should be soon. Okay? So this is what you should be doing. Okay. All right. So let's just see how this works. Well, you want to solve a minimum cardinality problem. This is hard. So instead what you do is you do this. Instead of minimizing the cardinality, you minimize the one norm. Okay? So subject to x and c. Okay? And there's nothing to tune here, right? There's no parameters, you just solve this problem. And the idea is that this often gives you something where x is quite sparse. It may not be the most sparse, but you get something that's quite sparse. And it's a simple method, anybody can do it. It's good enough. Okay. If you have a cardinality constraint problem, something like this. Here, this one, you might do it something like this. You could write it this way. And then beta becomes a knob you turn to control the sparsity. By the way, the sparsity is generally monotonic in beta, but not always. In other words, I can actually increase beta and get a solution which is more sparse, or the other way around there. I can decrease beta, so all sorts of weird stuff can happen. But generally speaking, beta controls the sparsity. Another one is you have an L1 regularizer problem. And so in fact, if you use an L1 regularizer now, in fact, one common name for it now, which is a good name because it reminds you what it's supposed to do. This is now referred to generically as a sparsifying regularizer. Right? So, Tikhonov regularization, that's gamma times the norm of x2 squared, is not a sparsifying regularizer. It's a regularizer, but it's not sparsifying. So, something like this, or the asymmetric, actually anything with a point at the origin, or if you know convex analysis, which you should, anything with a subgradient at the a subdifferential at the origin, which has non-empty interior. Anything that's got a sharp point is sparsifying. Okay, so that's the idea. And here you use beta as a knob or gamma as a knob, and you choose. Okay. Now this is something which some people in some applications do always, other people in other applications never do. And so I call it polishing. That's not a standard term. I just made it up. And I think other people now use this word, so I don't know. But, okay, here it is. The idea is this. Use the L1 heuristic to find the x outputs that require sparsity. So you turn your knob until you have, 120 bars in your truss out of 1,000,000 possible ones. Then what you do is you go, now that you know the sparsity pattern, you solve that small convex problem to get it exactly. Another way is you do the genetic study and you take 30,000 genes, you find the 27 that allow you to classify reasonably whether you have a disease or not. You find those 27. Then you go back and you say, suppose I pick those 27 from the beginning. Now you adjust the weights to get the best classifier. Okay? And that's the one you use clinically now. Okay? So you fix the sparse pattern and you just resolve it. Okay? Now, by the way, my friends in statistics say you should never do this. So, and I trust them. They know what they're talking about. They all seem they're actually the frequentists, not the Bayesians. The frequentists are completely aligned on this, and they say absolutely not, you shouldn't do it. I don't totally understand why it has to do with shrinkage. They refer to this, and they say the shrinkage is good. Leave it there. So I just thought I'd mention this. Oh, obviously in engineering design, there's no reason not to do this, right? If I'm designing an FIR filter, or if I'm compressing images, and I find out that there's 1,000 non-zero coefficients, I should go back and then update the coefficients to fit the image best before transmitting or storing. Okay. So now I'm going to give you a couple of interpretations. Why does it work? By the way, there's lots of intuitive reasons it works. One would be, you go back one is just that if you think about the L1 norm, it's, the absolute value, it's got this sharp thing. And so that means that the relative incentive to make something smaller is maintained all the way to 0, right? So, or then geometrically, if you draw an L1 ball and it's got all these points, and you minimize something, and the solution is typically on one of the corners, and the corners are sparse. Okay, so this is obvious. Okay, so here it is as a convex realization. Let's start with this problem. And here I'm going to assume that I have a bound on all of the entries. Okay, so it's R. And I'm going to write this as a mixed Boolean convex problem. So this is exactly equivalent to this one. Right? And here's what it is. I introduce a new vector, Boolean, which indicates whether x is 0 or not. Right? And so I put it like this. And this says the absolute value of x is less than 0 if z is 0. That means x is 0. Or it's less than r, but that's this constraint. So ahead of time, right? So it looks like that. And this is exactly this. It's exactly equivalent to that. Okay? Of course, you can't solve that any more than you can solve that. Okay? But what we're going to do now is a very simple thing. We're just going to do the convex relaxation. And convex relaxation here says I replace the set 0, 1, the 2 points, with the interval 0, 1. Then this is a completely trivial QP. Well, sorry, it's not convex in here. Okay, so here's the relaxation. I allow this z to be any number between 0 and 1, and I get this. But if you stare at this long enough, you can figure something out. Here, the optimal value of zi is simply absolute xi divided by r, because it's monotone in the objective, and the zi appears nowhere else except here. You know, so you would take zi is norm x is absolute value xi over r, and so in fact this problem is equivalent to that, and that's our L1 heuristic, right? So this tells you immediately that when you solve this and you put the factor 1 over r in, this gives you a lower bound on the original problem. Right? It's usually, by the way, a terrible lower bound, but at least it's a lower bound. Right? In other words, when you find that you find a truss you like with 120 bars, and you achieve some value of something, the gap is usually like a factor of 2 or 3 or 10 or something. It's not great. It's not something that would immediately say, okay, you can go home now. It's done. So this is the relaxation interpretation. There's another one, which is very interesting. By the way, I should, let me make one point here. Actually, let me just draw a picture over here to make this point. All right, that's good enough. And maybe consider lines up in line, highest contrast. Okay, so here's the cardinality function, right? It looks like this, and I'll try to draw it big so people can see. Right, so it looks like this. That's it, right? That's the cardinality function, right? And so, the L1 norm, in fact, and let's assume that there's a bound on how big x can be. So, let's put a bound on where x can be, so it only goes out to here, let's say. Okay, and here's the L1 norm. Right? So, no one would ever look at a function that looks like this, and look at a function that looks like that, and say, that's a good approximation of that. That's my point. Right? So, from this point of view, you have to say this whole method looks very implausible. You say, how can anything good come? You know, that's not... And look, if someone comes up to you on the street and says, oh, here's my function, you know, it looks like this, you know, it's slightly non-convex. You go, oh, no problem, we're just going to replace it with this. Right? You know, in that case, you would hardly be... Of course it's going to work, right? But it's not so obvious here, I think. Right? So, this is my point. Okay. But there's a beautiful interpretation of this. Here's the interpretation of it. It's the convex envelope. So the convex envelope of a function is this. It's the largest convex function that's an underestimator of it. And if you know convex analysis, it has some very simple formulas. Here's one. Actually, there really aren't any technical conditions here. It's just the conjugate of the function, non-convex functions, the conjugate of the function, conjugated. That gives you the envelope. And it turns out the largest convex function, less than card, on let's say -1, 1, is exactly the absolute value. So let's look at that here. This is here's 1 and -1, and I should have done this in a different color. I'm going to fix that now. So here's our original function, right? And now what I have to do is put a convex function below this. Okay? So I mean, then here's a terrible choice, right? There's one. Okay? That's terrible, right? So clearly, any convex function that's below this has to include this point, and it has to include that point, and so it's going to include that, like that, and I can't make it. There's nothing bigger, so that's it. So the absolute value is the largest convex, highest convex function that's an underestimator of the cardinality. Okay, so So that's
So the y with take plus minus 1.
good question. That's the next slide. That's a very good question. Okay? So now that you understand that, you can be much more sophisticated than the people who just blindly apply L1, which is basically 99% of people who use these methods. Okay? And it would include essentially all statisticians and anyone in machine learning. Okay? For that matter, it includes everyone who does bus design and things like that. So here it is. Suppose you had a better prior idea about the bound of each variable than just simply -1, 1 or -r, right? In fact, suppose you knew that x was between Li and Ui. Oh, by the way, if you're doing this over a convex set, is it easy or hard to find the bounding box of a convex set? Bounding box is the smallest box aligned with the axis that covers a convex set. Is it easy? Is it hard?
Easy.
How do you do it?
Just solve.
Yeah. You minimize and maximize xi. So in 2n, it depends on what the dimension is, right? But if the dimension is 100 or something, it's nothing, or 1,000, it's nothing. You maximize and minimize each xi, and you get the bounding box. So we can get Li and Ui, in fact, quite easily. Okay, in this case, you think about what is the convex realization? It says, let's discuss something simple here. If I told you that Li was positive, what would you know about xi? About card of xi in particular? It's 1. It's 1. It's all over, right? Xi is going to be non-zero because it's positive. And if Ui is negative, then Xi is negative, so it's irrelevant. So the only thing interesting here is when Li is negative or 0 and Ui is positive or 0, right? That's the only thing interesting. And so the convex envelope is very simple. I mean, you can see it, but let's just make this asymmetric now. Let's suppose for some reason I knew that this was truncated at 1/2, like this, right? In which case, the convex envelope would be this. Right? By the way, it then goes up to plus infinity because that's the boundary. Okay? And you can see what it is. It just looks like that. Okay? But you can imagine all sorts of other things. If there's more complicated sets on which you can compute the convex envelope of a card, you do it. Okay? Everybody? So it says that this is really the right thing to do. Okay? And not so that answers your question. Okay. Let's look at some examples. Let's do regressor selection. And by the way, here, I'm not using this fancy method. The fancy method here would be to use the asymmetric weighted. I'm using the traditional non-weighted one. Okay. So what we'll do is the heuristic for this is you minimize this. By the way, this has a name. I guess if you put a square there, but it's the same. It's called lasso, which is this least absolute something or other. Okay. And what you do is you fiddle around with gamma until you get card less than k. Then you fix the associated sparsity pattern, and then you solve the least squares problem. Okay? So let's see how this looks. This is an example from my book. I guess it's example 6.4. I mean, it's a small problem, right? Here it is. It's a regression problem in R10. You want to match a vector at R10. You're given 20 regressors, and you want to select. You want to get a good fit, and at the same time you want a small number, right? Some of these you can solve exactly. If I say figure out what is if I say what's the one of cardinality 0, that's simple. Cardinality 1, I just find the vector which has the smallest angle with respect to the column which has the smallest angle with respect to B, and so on. And in this case, we can get the exact, I mean, it's nothing because it's 20 choose 10, and that's not it's, in this case, to get the whole curve, 2 to the 20 is a million, and so it's not a big deal. And you solve a problem, a least squares problem of this size, anyone know? What's the number? How fast can you solve a regression problem of that size? See, this is not cool. You should know complexities and convergence theorems, but you sure as hell better know how these things work on real computers. Anyone know the number? Millisecond. Okay. This one? This would be probably, this is sub-microsecond. Okay? So, I think, by the way, I don't think these are, I mean, it's true, these are kind of things that, this is not theoretical, but it is important to know, because if you know these things, it affects what you think can be done and all that kind of stuff, right? So, this can be, I mean, it's nothing, this would be probably under a microsecond, right? So 2 to the 20s a million. So it says probably, if this was written in a real language, by the way, MATLAB, it might take about a year and a half to solve. But in a real language like C or something, this would probably be like a second or two, less. Okay. All right. So anyway, back to the story. This is the exact curve of optimum cardinality versus fit. That's fit. That's cardinality. Now this is what's really cool about this. It's actually kind of amazing. This is the L1. This is the curve you get from L1. Not L1, but L1 and then polishing. Okay? And actually it tells exactly the right story. Right? It says that it does pretty well. Right? So for example, for cardinality, well, I mean, it depends how you judge it. Right? Let's do it this way. For this level of error, that's the optimal, and it failed to find it, right? But it's, it's close, right? And in some cases, it did find the optimal, like here and here, here, and here, and here. There's not much to do there. So the idea is, it gives something that's okay, and I'm glad that this picture didn't come out with the two curves on top of each other. If they did, I would have to I'd have to choose another random example, because it would be not right pedagogically to show working too well, right? So this gives you the flavor. Okay. Okay. Let's do sparse signal reconstruction. So here, let's minimize this fit here, knowing that X is sparse. There's the L1 heuristic. Another form would be this. And this, I guess they call this basis pursuit denoising. They all have all sorts of secret names for these things. Basic pursuit, denoising. What do they have? Lasso. It goes on and on and on. And you classify them. They all have this form. Okay. Let's do an example. And these things are actually just kind of amazing. If you haven't seen this before, then you should prepare to be stunned. Okay, so these things are just magic, especially when you see how bad this is. I mean, this is not a good approximation over here, right? There'd be no reason to believe, if you have this picture in mind, any of this should work at all. But look at this. I have a signal that has 1,000 elements in it, but I know that only 30 are non-zero. But I don't know which 30. That's the problem, right? So, and for the record, 1,000 choose 30 is a very big number. Okay. So I have 200 noisy random measurements here of it, and I want to estimate X. Now, by the way, if someone walks up to you on the street or in your job or something like that and says, I have 200 measurements of 1,000 numbers, please estimate the numbers, you should avoid that person and that company. Okay? Definitely. Because this makes absolutely no sense. It'd be like the same, it'd be as if someone walked up down the street and said, I'm thinking of two numbers and they add up to 12. Please tell me what they are. I mean, this is idiotic. Everyone following this? Right? And so you should avoid these people, this is, okay. Then you can say, what you should say to a person like this, oh, excuse me, surely you understand that your problem is stupid. And that you must surely have some other information about X. Or otherwise or the two numbers, otherwise I couldn't tell you what they are that add up to 12, right? If they say nothing at that point, then definitely leave. Just turn around and walk away, right? Okay, so in this case they say, oh yeah, okay, fine. Here's some prior information. Okay. By the way, this is actually kind of interesting because if someone asks you to estimate 1,000 numbers on the basis of 200 measurements, it's a factor of 5 in the wrong direction, right? If it were reversed, it would be reasonable. If someone says, please estimate these 200 numbers, I have 1,000 measurements, that's reasonable, right? So if they told you which 30 were non-zero, this would be completely reasonable. If they said, please fit 30 parameters and you say, well, what measurements do you have? I have 200 noisy measurements. Makes perfect sense, right? So, okay. So, anyway, you just apply this method, and here's what happens. This is the original signal, right? You simply, actually a wide range of gammas works, and this is what you reconstruct.
You know realization of matrix A.
What's that?
You know realization of matrix A.
Absolutely, you know it.
We know.
Oh, by the way, someone, you thought the other one was stupid? If someone walks up to you in the street and says, please estimate these 1,000 numbers, I'll give you 200 measurements, and you go, well, that kind of goes the wrong way. Don't you mean estimate these 200 parameters with 1,000 measurements? And they go, no, I mean estimate 1,000 things with 200 measurements. And then you say, well, okay, I'll try. What's your matrix? And if they say, no, I'm not telling you that either, then it's definitely time to walk away. So, yes, you know it. Okay. So, and what's stunning about this, by the way, it's not exactly right. If you look closely, you can't see it. But, you know, these things are not lined up exactly the way they should be. The sparsity pattern, it nailed it. Right? So this is kind of extraordinary. Well, let's see. I'll just tell you, instead of quizzing you, I'll tell you how long it took to solve that problem. That one would be 1,000 squared. That would be a matter of milliseconds to solve. Okay? The L1 problem.
How do you choose gamma?
You choose gamma until it looks good. But if you think about it, this is the story in all regularization. People make up all sorts of big stories around it to make it sound more sophisticated. Like you say, I'm using no AIC information. Right? I don't know. You make up all... You know, the way to do it is by cross-validation or something like that. And a problem like this, you do it until it looks good. But if you don't want to, if you're embarrassed to say that, then you would make up some other big story about it. Throw in some fancy words and stuff.
And will the accuracy depend on your knowledge on the nature of V?
No, not very much. In fact, the gamma and actually the sigma is irrelevant, although it's not irrelevant. The sigma is part of the gamma. So in fact, this would work for any value of sigma. You just take a different value of gamma.
Okay, maybe it's a deterministic noise or just bounded or
Oh,
uniformly distributed. Is there any difference?
In this case, yeah, you would, instead of having a least squares criterion, you'd have some other convex criterion. Right. If you knew, for example, if V had Laplacian noise, this you'd minimize it L1 normal of AX minus V plus 1 L1 normal of X. Yeah. So okay. So this is how this works. It's kind of stunning. Oh, by the way, unlike least squares, which degrades graceful, right? These do not degrade graceful. They undergo phase transitions from working so well that you can't even believe it. That you have to check the code, that you're not doing something wrong, and actually that you're not plotting the actual original truth signal or something. They go from working unbelievably well to total and complete failure, undergoing with a phase transition. Okay, so that's very common for these. Okay, so here's the best Tikhonov regularization. I mean, but of course, come on, this is linear algebra, right? If I give you 200 measurements and ask you to estimate 1,000 numbers, your best job is just to say 0 and walk away or something, right? So your best bet. So there it is. Okay. Okay. Now I'll say a very small amount about some of these recent theoretical results. They're extremely interesting. Actually, I find the first bit interesting. The highest order bit is that you can say anything about these methods. Right? So that I find shocking. And I'm not going to go into this because you can there's about 10,000 papers written on this now. So you can find these instantly. But it's basically this. Oh, by the way, I should say the following. These methods work extremely well as very powerful heuristics, independent of any theory. The theory has nothing to do with whether or not it works in practice. And by the way, the theory covers an extraordinarily, vanishingly small part of the uses where you use it. Okay, so nevertheless, just the existence of any theory I find interesting. It's this. Now, if you're going to reconstruct X, well, I mean, you need at least K measurements because it's silly otherwise, right? So, and in fact, the question is, how much more than k do you need? Right? That's the question. So the question is, when does this reconstruct x exactly? And shockingly, there are answers. And it basically says that as long as A satisfies some properties, which are not mere technicalities, they're real properties, then it says that if you take a number of measurements, which is a small fraction more than the actual cardinality of what you're estimating, it says that this heuristic reconstructs x exactly with overwhelming probability. Okay, so that's just shocking, right? So it's amazing, right? It just doesn't make any sense, but it's true. And the valid A's would include things like random entries or a Fourier transform chosen at random and several other, things like that. So, actually, how many people have seen or heard of these things?
This class of Y, it is not some understood class, which is like, it's not one several classes which we can define.
They've settled on the main one is something called the restricted isometry property. So, and people repeat it enough so they think they understand what it means now. Actually, it's not that complicated. Yeah, you can look. This is Donahoe, Candes, Romberg, Tao. If you want to look more about these, I'm not going to say much more about it. Okay. Now we're going to move on to total variation reconstruction. This is from the 90s. And so here you would you want to minimize something like the norm or the norm squared. There, it wouldn't matter. You just get a different gamma. And this is the one norm. This is the total variation of a signal. It's the sum of the absolute values of the differences, right? And this is called total variation reconstruction. And this was a big deal in the early 1990s. It was used very widely to restore all sorts of things like audio. And in fact, it was a big deal when they took some wax cylinders, recordings of Caruso, and they actually restored them shockingly well. And it's just a quick example. This is also from the book. So here's a signal, got some kind of slow thing in these sharp, transitions like this. And here's the corrupted version, right? And so we want to take this and somehow get this out. And so if you were to do total variation reconstruction, you get this. And these would be for different values of gamma. Right? By the way, you can see exactly what's happening. If gamma is too high, you're moving towards piecewise constant, and you don't get the curved part. And these would be for two other values of gamma. But notice what is left here is the sharp transitions are preserved perfectly. Right? They're not smoothed in any way. And you got where they were, also I might add. You got the locations of the big shifts perfectly. Okay. L2 reconstruction, in contrast, looks like this. To damp the noise, L2 reconstruction, of course, is actually linear filtering. You have a convolution filter, not causal, it's symmetric. But you end up with something like this. And to damp the noise significantly, you end up completely ruining this sharp shift. So L1 is something that preserves edges, and in image processing, it's the same thing. It preserves edges. And so that's why it's used very widely. In fact, it's related to median filtering there. Okay. Let's look at another one. Let's do 2D total variation reconstruction. So I have a 31 by 31 grid, so I have about 1,000 variables. And the assumption is X has relatively few changes in value boundaries, right? And I have 120 measurements. So again, I'm in this ridiculous situation where I am undersampled by a factor of like 7 or 8 to 1, right? Again, I'm giving you 120 measurements. They're perfect, but that's fine. Of 1,000 things, and I'm asking you to tell me what 1,000 numbers are based on 130 measurements, right? Again, it's ridiculous, except for this prior. And so you want to write it something like this. And the truth is, this is not even right. You really want to do this. This is an approximation of the gradient using the x and the y derivatives. You really want to use a circularly symmetric one, but this is fine. You end up with this L1, an L1 problem that looks like that. It's a small problem with 1,000 variables, and you can solve this very quickly. And here it is. right? So it's basically perfect. Okay? And it is perfect. Right. It's ridiculous, right? That with 1,000 measurements, 120 measurements of 1,000 numbers, you can just reconstruct it perfectly. Of course, the signal does indeed have low total variation, right? So your regularizer did the right thing. Or a Bayesian, by the way, would interpret this a completely different way. A Bayesian would say that...
Excuse me.
Yes?
I was just curious, was this 120 sampled uniformly?
Well, no, what was the matrix? Completely random.
I mean, it's hard to believe that you've restored the edges so well.
It is hard to believe, isn't it? No, I mean, when you do these things, you actually have to go back and make sure, it's very easy writing a script. You make a mistake, and when you're supposed to be plotting this, you accidentally plot that, right? Everybody here knows that, right? So this, you could have accidentally plotted the true, because, you write the code that plots this thing, you copy those 3 lines down below, and it still says somehow you're still plotting X true, right? And you think, wow, this works well. It works well because you're plotting X true. No, this is really it, I promise. You have to, in fact, when you see this, you have to go back and check. Okay? So, yes, it's shocking. Yeah. Oh, and by the way, the reconstruction here is it's not merely very good, it's exact. It's perfect. Because there was no noise in the original thing. So, this just gets it exactly. Right? And I guess that theory tells you this is not an accident by any means. Right? So, it's crazy, right? All right. So, here's the L2 reconstruction. It's what you expect, I mean, look, it kind of makes it, well, you're 8x undersampled, right? So the idea is you have a whole bunch of random linear functionals of this thing, and the ones that have a big support in the middle are big. And so, kind of after 120 of these, you have the idea that something is big in the middle, right? But you don't know, something's big in the middle, but other than that, you don't know. So anyway, so if you haven't seen these things before and you haven't figured out, you should be you should either be very disturbed by this and very impressed, right? Because if you have incorporated your linear algebra knowledge deeply as a working knowledge of linear algebra, this should be deeply upsetting to you. Because since you were a child, people have told you you cannot. If you have 20 equations and if you have 20 equations and 30 variables, you cannot find all the variables. I mean, this is obvious, right? So this should bother you to your core. Either that or you're not listening or not thinking, or something like that. So if you're not bothered, something's wrong. You should be bothered by this. Very bothered.
It's kind of unfair to compare L2 to
Totally
L1 on this specific problem.
Yes.
Because you know something about the
It's
nature
totally-
of the functions.
Totally unfair, exactly. Completely unfair. That's exactly right. Right. So, yes. No, it's not like this is some magic thing that works, but it is also at the same time true that I can describe what's happening here. I can describe what's happening here, and I can put it in a way that sounds ridiculous. I can say, I just estimated perfectly 1,000 numbers based on 120 measures. And it's true, I did. And that should bother you deeply. Now, the fact is, I added a prior. I have a prior, if you like, for Bayesian, or I added a total variation regularization, and it turns out the actual thing I was estimating does have very low total variation, right? Because, in fact, it only has a support on this circle, so that's it. But it's kind of amazing, I think. Yeah, so, okay. So now we're going to talk about some more advanced methods. So the iterated L1 heuristic, this is actually quite interesting. It goes like this. It says, let's set all the weights to 1, or you can set all the weights to the appropriate values from the bounding box, right? That's the really sophisticated method. And what you do is you're going to minimize a weighted L1 norm, and you're going to update the weights this way. Whenever an x is small, this is going to be really weird. When an x is small, you're going to increase the weight. And when x is big, you're going to decrease the weight. Now it sounds weird, but it's correct. The idea is this. when you minimize the L1 norm, if x came out big, well, probably it's non-zero. If it's non-zero, then screw it. Forget. Then you're penalizing it though by this weight. You should reduce the weight. If it's going to be non-zero, it might as well do what it wants, right? If it's small but not non-zero, it's a target for elimination, and you increase the weight. Everybody got the intuition? So that's it. Okay. So this typically converges in 5 or fewer steps, and it gives a modest improvement over the basic one. So it actually works quite well. And you can interpret this as the following. In fact, I'm going to draw a picture. So the picture is, let's look at the one-sided version. So x is positive. So it's this. Okay, so we only look here. So here's the card function. It looks like it's 0, and then it's 1. That's the card function. And the idea before was that we put a convex function that look like this, right? There. But what we're going to do now is I'll say, look, I'm going to get a much better fit. I'm going to find a smooth function that looks like this. Right? Like that. This, you would say, that's a much better approximation of that, right? Much better. Only minor problem with this is it's not convex. Right? So if I take this to be log with a little epsilon in there, then if I have this function, it looks like this. Okay? And the good news is it's a much better approximation of the card function, and the bad news is it's concave. So, okay, fine. So what I do then is, how do you solve a concave, how do you minimize a concave function over a convex set? That's very easy. Very simple method. You do the following. You linearize the concave function, right? And you minimize that over the convex set. You need no regularization, no proximal, anything. No step size, nothing. And you do it again and you repeat and repeat. And this goes to a local minimum. And if you apply that to this function, then you'll get exactly the weight update. So here it is. Here's your weight update. And that's the idea.
But we can't guarantee anything.
No. But you know what? We left all the guarantees. We stepped out the door of the safety of convex optimization and actual solving. On the third slide, when I showed it was NP hard, we stepped out of the safe area, and we stepped into the wild jungle where you can say nothing. Well, except there was that one little island, that safe island from Candes. But that's a tiny little place in this big jungle.
But
So.
maybe here we can also say something with large probability we get something.
I hope so. I hope so.
But
Yeah.
I don't know. At the moment.
As far as I know, not one. Not one. So, yeah. Actually, I heard a rumor that there is one, but I don't know what it is yet. So, okay, that's it. Okay. So let's see how it works. And this is very typical. So here's an example. I have a polyhedron here, which is it's 100 by 50. So it's got 100 faces, up to 100 faces, I should say. And I want to find the minimum cardinality point that is in this thing. Oh, and by the way, we ran branch and bound on this, and we found that the minimum cardinality is 32, right? This required, if I remember correctly, something like 32,000 linear programming solves. And it's boring, but you can guess how long that took. I won't make you do it. But that's in the microsecond region, so we did it fast. But nevertheless, after 32,000 LPs, we were able to prove that the minimum cardinality is 32, which is here. This is the L1 heuristic, right? So the first one gives you 44, and that's not so great compared to 32, frankly. But, I mean, L1 is a heuristic. You do the iterated reweighted one, and you get down to 36. And this also tells just the right story, that this is also a heuristic. It's not, and in fact, if on this data, if this number had equaled that, I wouldn't have shown it on the slide. I would have gotten another example where there was a gap. Because I do not want to give the impression that these methods solve the problem always, because that's false. Okay? What they are is they're just very good heuristics. And it's not bad getting to 36 instead of 32. If this took, if the effort to find this cardinality of 36 took, let's see, how long did that take? That took something measured in like a millisecond, as opposed to something that's 32,000 times more effort. So, okay. Okay. Let's look at an example. It's detecting changes in the time series model. Actually, we don't so here you have a time series model, and this is just very simple. It's an AR2 model. But it's time varying here. Right? So, and the assumption is that these coefficients here, they're piecewise constant and they change infrequently. In other words, their differences are sparse. Right? So that's the idea. And I'm given y, and I want to estimate these two things, right? And the heuristic is this. I'll tell you what the true maximum likelihood problem would be this. This is the negative log likelihood function for Gauss for the V, right? That's exactly what this is. And then to this you would add something involving the cardinality of the difference, right? And that would be the correct, that's the actual maximum likelihood estimate. Instead, we replace it with the L1 heuristic and we get this. And we vary gamma to get trade-off in the fit versus the number of changes in A and B. And in fact, it's quite beautiful. If I make gamma large enough, this is an exact penalty, for those of you who know convex optimization. That's an exact penalty. And that says that if gamma is large enough, this term will be 0. Right? Not asymptotically. There's a finite value of lambda, gamma, above which it's just 0. And that means, actually, it's beautiful interpretation. That means fit the entire data with one AR2 model. As you turn down gamma, it will split into 2. And now you've segmented the data into 2 parts, and you set one model in one and one in the other, and then you'll have 3 and then 4. Everybody see what I'm saying? So let's see how this works. Here's an example. I mean, this is a silly example, but it goes without saying. This works with matrices and things like that, where no human being could ever come close to doing this. I mean, not even close. So here's the data. It's an AR2 model, and here what happens is at t equals 100, A changes, and at t equals 200, B changes. And look, even especially now that you know the truth over here, and you look over here, and sure enough, if you take the first third and the second third and the third third, your eyeball looks at it and says, I detect a change in spectrum. You have to have your eye trained to detect spectra. But when you have your intuition about spectra trained, you will see that this has got some kind of like nice regular oscillations. This has got some higher frequency stuff. This is smaller and it's got some weird low and high frequency stuff. Okay, right? So the idea is we're going to take this data and try to reconstruct this, right? This is a silly problem, but of course, if these were matrices and this was an AR5 model, no human being could even come close to it. I mean, not even close to doing something like this, and the method would work perfectly well. So here it is. Here is the total, that's the total variation method. That's what gamma equals 10. And you can see all sorts of interesting things. First of all, it figured out that something big happened at 100. It knows something happens around here. It's got a lot of false positives. It's got some jumps here and here, and there's one here, and various things. If you do that iterated weight update, it's beautiful what happens. There's a big jump here, and so it says, fine, you're really a jump. And that allows this thing to float up. And it cleans up all of this, and you get this. And it's just beautiful, right? If you take a look at that. Basically, it nailed it. Now, it didn't get it exactly, but of course not. You're estimating the parameters in a stochastic process. You cannot, of course. But look at this. This one, I think it got, maybe, by the way, this is not exactly at 100. It might think that it's at 101. Over here, it was off by a little bit, right? And it didn't get the steady values exactly right, but I mean, these are unknowable. These are unknowable. These things you can't do. So it's actually fairly impressive, right, what this does. Okay. Everybody got that? So, and let me repeat. For that little baby problem, you're better off just looking out with your eyeball and saying, oh, something is happening different here, here, and here, and then fitting separate models. Fine. But if these were matrices and this was like AR5, forget it. Okay. Last topic is extension to matrices. So this is a huge big deal now. A lot of people are working on this and so on. And it's interesting. So the analog of card for vectors is rank, right? Because both of them measure, actually both of them, it's very interesting. Both of them go back to like Occam's razor, which is model complexity, right? And so if a model is a sum of a number of terms, then you know the smaller the number of terms, the simpler the model. And rank is the analog of that, right? Because it basically says you have a matrix, but all the action goes down in 5 dimensions, right? So that's the interpretation of rank. Now, a convex rank problem is the same thing, except you have rank. And if you have diagonal matrices, well, the rank is the card. And the analog of the L1 heuristic is the dual of the spectral norm. Instead of the maximum singular value, it's the sum of the singular values. It's this. And if X is symmetric and positive definite, this thing is nothing but trace. So in a lot of cases, if a matrix is positive definite, if you see trace in the method, that should be thought of as, well, in fact, I'll put it in a sophisticated way. Trace X is the convex envelope of the rank of X on the set of symmetric, positive semi-definite matrices with norm less than 1. Period. So that's what that is.
Frobenius norm.
For what?
Frobenius norm.
Actually, in both Frobenius and operator norm, I think it's the same. I think. So that might not be true, but it sounds true. So, and it could be true. Okay. So we'll do one last example, factor modeling. So factor modeling is you take a matrix, this is extremely widely used. You have a matrix, which is positive semi-definite, and you want to write it as a low-rank part plus a diagonal model, right? So this is universally used in finance. This is the only model ever used. It's universally used in actually educational studies. This is basically the only model they use, right, for regression. So, and you can interpret it lots of ways. The idea is it says that you're seeing vectors in Rn, but they're really being generated by a low-dimensional process here, mapping through a skinny matrix. And then V is an independent noise. And in finance, I think they call the Z's the factors. And they call the entries in D, they call them the idiosyncratic risk. Meaning it's sort of the variation in that single asset that has nothing to do with anything else. So it's idiosyncratic risk. Oh, by the way, if D is a multiple of the identity here, then it's trivial to express something this way. It's called the eigenvalue decomposition, right? So that problem is easy, right? If this has that form. But when the entries vary, it's actually hard when they have different entries. So here's a model with the fewest factors, is you write it this way. You write X plus D is your total approximation of sigma or something, and sigma is in C, and that's the idea. So, okay. And it could be anything. I mean, it could be things like Kovac-Leibler divergence or something, and then the trace heuristic just looks like that. And by the way, there's an iterated weight version of this as well. So let's look at an example. And the example is I generate 3,000 samples from a factor model. There's actually only 3 factors, and they're 20-dimensional vectors. The set of approximate, I just use this. Why not? Doesn't matter. And then we simply solve this problem. By the way, this is not the iterated one, right? The iterated one would do way better, but this is good enough. So this is it. And I vary beta. And here's the trace. These are the trace of all the eigenvalues of X. If beta is too small, you have a whole bunch of eigenvalues. And you can see when something jumps down like that, it's an eigenvalue going to 0. And the rank drops. And you can see something interesting here. I mean, your eyeball at this curve focuses on this point here, where you have knocked out all but 3 eigenvalues. And your eyeball also on this curve goes to this point, which corresponds to a rank of 3, right? So let's just take that point. And check. When you do that, you actually get the D's within 7%. And you actually have estimated the subspace actually quite well, like within 7 degrees or something like that. By the way, this is not the iterative reweighted one. The iterative reweighted one would probably make this half that value, right? And estimate these better as well. Okay, so that finishes up this topic. I'll just make a couple of conclusions. So these problems with cardinality and ranking, they arise in lots of cases. They're hard to solve exactly. But these heuristics they're convex, therefore solvable, and they give very good results in practice, and they're the basis of tons and tons of stuff. So that's it. That's the whole thing. Now you know about L1 methods.
Okay, thanks.
Yeah.
I have a question about the computational burden.
Yeah.
Because on the last example, you have this covariance matrix, which is 3K by 3K. You have to invert it, etc.
It is here. No, which one? This one?
Yeah.
No, sigma is
What
in this particular instance. It's 20 by 20. Right. Sigma is 20 by 20.
Oh, okay. Okay.
Yeah.
Well, anyway, then in the previous examples, when you want to reconstruct the linear fit, you need this three-diagonal D matrix.
Here.
1 minus 2, 1, something like that.
Oh, sorry, not in here.
In the earlier slides.
In the total variation.
Yeah.
Yes. Yeah.
And then you have, I guess, to invert it as well in the numerical method. And if the number of samples you observe is big, then it looks extremely complicated numerically.
Well, wait a minute. If you're just doing total variation reconstruction in one dimension, it's completely trivial. It's the opposite. It's as simple as it could possibly be. Because the matrix involved is tri-diagonal. And then all the matrices you would solve for any convex optimization method, interior point, subgradient, anything at all, they would all be banded. And we can solve banded equations unbelievably fast. So one-dimensional total variation and other type things and piecewise linear fitting, we can solve one. I can easily solve a problem with 1 million variables on my laptop in seconds.
And what about 2D?
2D is harder. Yeah, 2D is harder. And if you throw in anything in there that destroys the bandedness, then it's ruined, right? So yeah, that's an issue. I mean, there are methods for the 2D and other higher cases, but they start getting kind of complicated. But there, in that case, if anything throws off that bandedness,
Yeah, we got the special structure.
then it's ruined.
Okay. Yes,
Yeah.
Well, you talked about problems of offline,
Yeah.
like what about online?
Oh, you saw one yesterday? The robust Kelvin filter. Yeah. So you've all seen these methods used online. The robust Kelvin filter. Yeah.
No examples here.
Uh-huh.
Well, so it was difficult for the
What's that?
for example,
For here. Yeah.
the
Oh.
question is, should we apply the new samples, for example?
Oh, can you do that's a very good question. Can you do a recursive update like you can with least squares? My claim is, actually, we were talking about that yesterday. Then let's take this problem specifically. So let's do the following. Let's solve this problem in real time. So every second, although frankly, I can do the following. Every 10 milliseconds, at 1 kilohertz, I can get a new sample, and I want you to segment. I want you to do this as new data comes in. Okay? So Kelvin filter, you have a modest state, and you update. Here, it's actually very simple what to do. And this is also a perfect example of the point that you raised as well. If you look at this optimization problem here, it's L1, it's got least squares, but it's complete, this is banded structure, right? The only thing that ever talks to anything else involves, A, T, and BT get coupled here. And here, AT and BT get coupled to AT minus 1 and AP, they get coupled. So if you think of the nonlinear coupling in this problem, it's banded. That means this problem can be solved in linear time. Which is completely, it means I can solve this for 100 samples in way sub-milliseconds. That'd be I can solve that in microseconds. Maybe hundreds, but in hundreds of microseconds. So now, how do you do it? How do we implement something where new data comes in? Very simple. I maintain a list. I use a sliding window, which is 100 samples in the past. Those 100 samples in the past, I'm willing to change my mind for 100 samples. So if all of a sudden I'm doing something and I get new data, it might take me a while to figure out that a change has happened. When the change happens, I will go back and I'll revise my model, right, in the past. But what I do is I never revise anything. So when a period of 100 samples, if you're more than 100 samples old, you commit to your model and you never go back and change it. This will work perfectly. And I could run this at a kilohertz easily, and if I wanted to run it a lot faster, I could. So, but that's a great question. So it's not as straightforward as just running a Calvin filter. Yeah?
Yeah.
There are a lot of different problems, and the question is, are there any results or thoughts how cardinality changed these keyword parameters, gamma, for example? Are there something in common in this?
Right. So statisticians do these beautiful plots where they plot the parameters as a function of the gamma or whatever it is, or lambda. And you can actually see things like, in fact, it's like the last picture I showed where you can see them going to 0. But they have really, every now and then things happen where a parameter will actually become 0 in a statistical model. You increase gamma and all of a sudden it will become positive again, or non-zero. So it's not monotonic, it's just generally monotonic, the cardinality. And I don't know how much is known about that.
Yeah.
Are there any ways to find out if, whether the L1 heuristic will work for some particular problem?
Which definition of work?
Will give some good result.
Again, that's two. Right. Do you mean a mathematician's definition, or do you mean somebody doing something?
I think I mean
Which one?
somebody.
You mean that what physicists never do is doing something.
No, but let me ask you. I'll ask you.
The second.
Are the computational complexity police in the room with you at the time? Are they? No. Okay. So, how do you know in practice? I think in this case you just do it, as far as I know. So, I mean, there are these results. The results apply very narrowly and not to many practical problems. As far as how to do it theoretically, I think you have to read these 10,000 papers on.
No, I meant practically.
Oh, practically. Ah, thanks. Good. Okay, fine. So then, no, you just do it, is what you do. And of course, you do it by first simulating things that really are sparse and fit the model. Because if it doesn't work on your simulated data, then it's not going to work on real data. Then you try it on real data. And then you rehearse what you're going to say when someone says, "That's amazing. Is this really?" If you've estimated something and you say, "Wow, is that really true? If I drill here, there's going to be oil." Then you have to rehearse a story like, "Well, you must understand these are just heuristics. We firmly believe that there could be oil there." Anyway, so
With probability.
with overwhelming probability, which might not happen after you drill the well. So.
Okay.
Yeah.
You told a lot about like practical applications, so my question could be strange, but while I'm working in the adaptive control field, there is always a problem. When we have a system with a lot of parameters, and we need to estimate it, right? And we have to follow this persistent excitation condition and so on, and we never have like a good convergence of all parameters.
Right.
We have a convergence just of some parameters. Can we use just with cardinality problems to have a basement which parameters we need to converge to follow the system dynamics, or?
Sure. Yeah, sure. Go ahead and you should introduce L1 methods into adaptive control. There you go. And the story would go like this. I'll write the abstract for you. Right? The story goes like this. In adaptive control, it works if there's 3 parameters or maybe 4, and it doesn't work when there's 12. Everybody knows this, right? Then you'd say, we're going to show you how to make it work with 12, except we're going to put L1 regularization. So what's really going to happen is we're going to choose 3 out of the 12. There you go.
Maybe the last question about matrices. So you said that rank is a natural extension of cardinality to matrix case, but we use other analogs of cardinality, say the number of non-zero rows, number of non-zero columns, and it works.
Oh, I'm glad you said that. because there's one thing missing from these slides and I forgot to add it. Okay, so there's another generalization of this is when you don't want a single vector, a single entry to be 0, but you only get the benefit if a group is 0, like a row or a column. Right? Okay. So there's a perfectly good method for that. It's called sum of norms. You take the sum of norms, and it works extremely well, and I should add them in these slides, and I'm lazy, so I haven't. But I should, and I'm glad you asked the question. And by the way, in statistics, it's called group lasso.